Hey everyone, and welcome back to AI Paper Podcasts. Today we're going to be diving into Ladder, self-improving LLMs through recursive problem decomposition. It's a fascinating paper published just last week on March 6th, 2025. Now, before we kind of unpack all the details for our full deep dive crew, let's give our short form viewers a quick rundown of the key findings.
Absolutely. This paper tackles the challenge of making LLMs better problem solvers, particularly in the realm of complex reasoning. And they use mathematical integration as a testbed because it requires sophisticated logic and has a clear right or wrong answer.
Exactly, and they achieved some pretty remarkable results. First off, Elliter boosted the accuracy of a Llama 3B model on undergrad-level integration problems from a measly 1% to a whopping 82%. I mean, that's a massive leap.
And they didn't stop there. They took on the MIT Integration B, which is notorious for its difficulty even for seasoned mathematicians. Using a Qwen 7B model trained with Elder, they achieved 73% accuracy, outperforming much larger models.
But here's where it gets really interesting. They introduced this concept of TTRL, or test time reinforcement learning, which essentially allows the model to learn and adapt during the test itself.
It's like the model is studying the textbook as it takes the exam, getting smarter with each question.
With TTRL, their Qwen model achieved a mind-blowing 90% accuracy on the MIT Integration B, even surpassing OpenAI's O1 model.
Keep in mind that Owen didn't have access to the same numerical verification tools used in this paper, so it's not a perfect apples-to-apples comparison. But still, these results are incredibly exciting and suggest a paradigm shift in how we approach AI learning.
All right, that's the TLDR for our short-form friends. If you want to learn more about how LLD and TTRL work, stick around for the full deep dive. We're going to unpack the technical details, explore the implications, and discuss some potential future directions.
Let's start by digging into how LLD actually works. The paper highlights a key challenge with current reinforcement learning methods, finding that sweet spot of difficulty for the AI to learn effectively.
Right? It's like Goldilocks and the Three Bears. Not too easy, not too hard, but just right. If the problems are too simple, the model doesn't learn anything new. But if they're too complex, it gets overwhelmed and fails to make progress.
Exactly, and this is where Elliter comes in with a really clever approach. It allows the AI to create its own difficulty gradient, breaking down a tough problem into simpler versions.
It's almost like the AI is building its own curriculum, starting with the basics and gradually working its way up to the more challenging material.
Imagine you have this incredibly difficult integral to solve. Elliter takes that problem and recursively decomposes it into a series of simpler integrals, creating a kind of branching tree structure. You have the original problem at the top, then slightly easier variations branching up below, and even easier variations below that until you reach a level where the AI can easily solve the problems.
So the AI is essentially generating its own practice problems, starting with the easy stuff and progressively tackling harder and harder variations until it can conquer the original challenge.
Precisely. And there are some clever techniques involved in generating these variants. The researchers use methods like temperature cycling to control the randomness of the variations, different personas for the AI to generate from, and batching to create a diverse set of problems.
It's like a whole system for creating personalized AI training regimens tailored to the specific strengths and weaknesses of the model.
Now, of course, you need a way to make sure the AI is actually solving these problems correctly, right? You don't want it just spitting out random answers and thinking it's a math whiz.
Right. That's where solution verification comes in. The paper describes a multi-point numerical approach. Essentially, they pick a bunch of points within the range of the integral and check if the AI solution matches the actual value at those points.
It's a robust way to ensure the AI isn't just getting lucky or gaming the system.
Once you have this verification mechanism in place, you can then use reinforcement learning to actually train the model. The paper uses an algorithm called GRPO for this purpose.
We won't get too deep into the technical weeds here, but essentially, GRPO is a way to reward the AI for getting closer to the right answer and penalize it for straying too far off course.
So it's like giving the AI a little pat on the back when it does well and a gentle nudge in the right direction when it starts to wander.
Exactly. Now let's take a look at those Llama 3B experiments. Remember, this is a model that started off solving only 1% of the undergrad level problems.
But after training with LDO, it achieved an 82% accuracy rate. That's a night and day difference.
And the paper highlights the importance of those generated variants. When they trained the model without using variants, it struggled to handle the complexity of the problems and failed to improve significantly.
It really shows how crucial that step-by-step learning process is, allowing the AI to build up its problem-solving skills gradually rather than being thrown into the deep end right away.
Now let's move on to the MIT Integration Bee, where things get really exciting.
This exam is designed to be brutal. It's not just about memorizing formulas, it's about applying mathematical concepts in creative and often unexpected ways.
And remember, they used a Quinn 7B model for these experiments, which is larger than the Llama model, but still relatively small compared to some of the giants out there.
Even with just ladder training, they achieved a 73% accuracy rate, which is already impressive considering the difficulty of this exam. But then
they unleashed the power of TTRL, that test time learning magic we mentioned earlier.
And boom, the accuracy shot up to 90%, surpassing even OpenAI's O1 model.
It's a remarkable achievement. Now, as we mentioned before, O1 didn't have access to the same numerical checker used in this paper, so it's not a perfect head-to-head comparison.
But it still highlights the potential of ladder, combined with TTRL, to push the boundaries of what's possible in AI problem solving.
One crucial finding is that TTRL only worked effectively after the model had been trained with Eller. It's like Eller provided the foundation, giving the model the core knowledge and problem-solving skills it needed to then adapt and improve on the fly with TTRL.
It's a two-step process. First, you build a strong base, and then you empower the model to learn and adapt in real time.
Precisely, it's a powerful combination that opens up a whole new world of possibilities.
But before we get too carried away, let's take a moment to appreciate what makes TTRL so special. It's not just about brute forcing the problem by trying every possible answer until something sticks.
Right. It's about using those generated variants to actively learn and adjust during the test itself. Imagine the model is saying, okay, I'm stuck on this really tough integral. Let me generate some easier versions, practice on those, and see if I can use those insights to crack the original problem.
It's like the model is having a series of aha moments as it works through the test, constantly refining its understanding and problem-solving strategies.
And the researchers observed that the model's ability to solve those really challenging problems on the MIT exam was in some cases quite unexpected. Even they were surprised by the model's insights and problem-solving approaches.
That's fascinating. It suggests that LDR might be enabling a form of emergent intelligence where the AI is developing its own unique ways of understanding and solving problems that go beyond what we explicitly programmed it to do.
It's like the AI is developing its own mathematical intuition, finding elegant solutions that even seasoned mathematicians might not have considered.
Okay, I think we've officially blown our minds for part one. We've explored the key findings of the LDR paper, delved into the technical details, and started to grapple with the implications of this work.
Welcome back to AI Paper Podcast. Before we went to our short form segment, we were discussing the impressive results achieved by LDR and TTRL on the MIT Integration Bee.
Hitting that 90% accuracy mark with the 7B model is seriously impressive, especially given how tough that exam is. But as with any groundbreaking research, there are always limitations and areas for further exploration.
Absolutely. One thing the authors acknowledge is the computational cost of TTRL generating and solving all those variants at test time requires significant compute power, which could be a barrier to practical implementation in resource-constrained environments.
Right. It's not something you can just run on your phone yet.
Yeah.
But I wonder if there are situations where the computational cost might be justified, even with current hardware.
That's a great point. Imagine scenarios where even a small improvement in accuracy could have huge implications. Things like medical diagnosis or financial modeling, where even a fraction of a percent can make a big difference in those cases. The extra compute might be a worthwhile investment.
That makes sense. So the computational cost is a consideration, but not necessarily a deal breaker. What about other limitations? Are there any fundamental constraints to this approach?
Another limitation to consider is the reliance on a reliable verification mechanism LDR and TTRL work, because they have a clear way to check if an answer is right or wrong. But what about tasks where the correct answer is more subjective or open-ended?
That's a great question. Like, how would you apply this approach to something like creative writing or musical composition? There's no single right answer. It's all about style and interpretation.
Exactly. So extending this framework to more nuanced domains would require some creative thinking about how to define and measure success. Maybe instead of a binary right or wrong, you have a spectrum of quality or a set of criteria that the AI can aim for.
Perhaps you could use some form of human feedback to guide the learning process, at least initially, like have experts rate the AI's outputs and use those ratings as a reward signal.
That's an interesting idea. It could be a way to bridge the gap between objective verification and subjective evaluation, providing a sort of training wheels for the AI as it learns to navigate those more creative spaces.
Another area I'm curious about is exploring different types of variant generation. The paper focuses on mathematical transformations for integration. But what about other types of transformations that could be applied to different tasks?
That's a key point. The authors themselves suggest that any domain where question variants can be generated, and there is a gap between the ease of verifying and generating solutions, could benefit from ladder, for example. Instead of just simplifying mathematical expressions, you could imagine transforming images, text, or even code to create those difficulty gradients.
So for image recognition, you could start with a clear, high-resolution image, then gradually add noise blur or occlusions, forcing the AI to work harder to identify the objects.
Exactly. Or in natural language processing, you could start with simple sentences, then gradually increase the complexity of the grammar and vocabulary, pushing the AI to grapple with increasingly nuanced language.
It's all about finding creative ways to scaffold the learning process, providing just the right amount of challenge at each stage to keep the AI engaged and progressing.
And I think that's the beauty of ladder. It's not just a specific algorithm. It's a framework for thinking about AI learning that can be applied across a wide range of domains.
Yeah. It's a paradigm shift from traditional supervised learning, where we feed the AI labeled data and expect it to learn by rote. Instead, we're giving the AI the tools to become self-directed learners, to explore and master complex concepts on their own, generating their own learning materials along the way.
It's like we're moving from a teacher-centric model of education to a student-centric one where the AI is empowered to take ownership of its own learning journey.
So if we zoom out a bit, what are the broader implications of this research? What does it tell us about the future of AI?
Well, I think it suggests that we're moving towards a future where AI systems are not just tools, but collaborators working alongside us to solve complex problems and push the boundaries of human knowledge.
Instead of simply following our instructions, they'll be able to learn and adapt alongside us, bringing their own unique insights and problem-solving strategies to the table. Imagine working with an AI that can not only process information faster than any human, but can also generate novel ideas and solutions, constantly expanding our understanding of the world.
That's a compelling vision, but it also raises some important questions about the nature of collaboration and the evolving relationship between humans and AI. How do we ensure that these AI collaborators are aligned with human values and goals? How do we foster trust and understanding between human and artificial minds?
Those are big questions, and they're not ones that we can answer definitively today. But I think it's crucial that we start asking those questions now as we develop these increasingly sophisticated AI systems.
Absolutely. Responsible AI development isn't just about technical prowess. It's about thoughtful consideration of the ethical and societal implications of our creations. We need to approach this technology with both excitement and caution, recognizing its potential to both empower and disrupt.
And that brings me to a point in the paper that I found particularly intriguing. The authors mentioned that the model's ability to solve those really tough integration problems on the MIT exam was in some cases quite unexpected. Even they were surprised by the model's insights and problem-solving strategies.
That's a fascinating observation. It suggests that ladder might be enabling a form of emergent intelligence where the AI is developing its own unique way of understanding and solving problems that goes beyond what we explicitly programmed it to do.
It's like we're seeing glimpses of a new kind of intelligence, one that isn't bound by the limitations of human thought. It's both exhilarating and a little bit unsettling.
It reminds us that we're still in the early stages of understanding the full potential of AI. We're creating systems that can learn and adapt in ways that we never imagined, and it's up to us to ensure that we guide their development responsibly.
Okay, I think we've covered a lot of ground in this segment. We've explored the limitations of LR, discussed some potential future directions, and started to grapple with the broader implications of this research for the future of AI and the relationship between humans and intelligent machines. But our deep dive isn't over yet. Welcome back to AI Paper Podcasts. We've been unpacking Elder, this groundbreaking framework for self-improving AI. And I don't know about you, but my mind is officially blown. We've talked about the technical achievements, the limitations, and even touched on the philosophical side of things. But now I think it's time to really grapple with the big picture. What does this all mean for the future?
You're right. It's not enough to just marvel at the technical brilliance. We need to consider the broader implications, the potential benefits, the risks, and the ethical considerations that come with creating AI systems that can learn and evolve so rapidly.
Okay, so let's start with the good stuff, the potential upsides. What are some of the positive ways LR and TTRL could impact the world?
Well, imagine a world where scientific discovery is accelerated by AI systems that can generate and test hypotheses at speeds we can barely comprehend. Think drug discovery materials, science, even fundamental physics problems that have stumped humans for decades could potentially be cracked by AI working alongside us.
That's a powerful vision. It's not just about replacing human scientists, but about augmenting our capabilities, pushing the boundaries of what's possible through collaboration between human and artificial minds.
Exactly. And it's not just about science either. Think about engineering optimization problems, designing more efficient transportation systems, managing energy grids, even personalized medicine tailored to an individual's genetic makeup. Lander's approach could revolutionize countless fields.
It's like we're giving these AI systems the tools to become master problem solvers, and then stepping back and saying, okay, show us what you can do.
And that's where the show us what you can do part gets a little tricky. Because while the potential benefits are enormous, we also need to be acutely aware of the risks. And I'm not talking about sci-fi robot uprising scenarios, but rather the more subtle and insidious ways this technology could go awry if we're not careful.
So let's talk about those risks.
Right.
What are some of the concerns that people have raised about AI self-improvement?
One of the biggest concerns is the potential for bias to be amplified and perpetuated. We know that AI systems are only as good as the data they're trained on. If that data reflects existing societal biases, those biases will be baked into the AI's decision-making processes. And with self-improving AI, those biases could potentially become even more entrenched as the system refines its models based on flawed data.
It's like a feedback loop where the AI learns to be prejudiced, and the more it learns, the more prejudiced it becomes. That's a scary thought.
Yeah.
We need to be incredibly vigilant about ensuring the data used to train these systems is diverse, representative, and free from harmful biases.
Absolutely. And it's not just about the data itself, it's about the goals and values we embed in these systems. If we're not careful, we could end up with AI that optimizes for narrow objectives without considering the broader ethical implications. Imagine a system designed to maximize profits, but it does so by exploiting workers or harming the environment. That's not the kind of future we want.
It's like giving a powerful tool to someone who doesn't understand its full potential for harm. We need to think deeply about the ethical frameworks that will guide the development and deployment of self-improving AI, ensuring that it's aligned with human values and used for good.
And that's where the real challenge lies. It's not just a technical problem, it's a philosophical one. We're essentially grappling with the question of what it means to be human in a world where machines are becoming increasingly intelligent and autonomous.
It's like we're writing a new chapter in the story of humanity, and we're still figuring out the plot. But one thing's for sure, this is a conversation that needs to involve everyone. It's not just for AI researchers and tech companies, it's for policymakers, ethicists, social scientists, and frankly, everyone who will be impacted by this technology, which is all of us.
You're right, we need a multidisciplinary approach to navigate these complex issues. It's about bringing together diverse perspectives, having open and honest conversations about the potential benefits and risks, and ultimately working together to shape a future where AI serves humanity rather than the other way around.
This whole conversation reminds me of something Carl Sagan once said: "We are a way for the cosmos to know itself." And now we're creating AI that could potentially become another way for the cosmos to know itself, maybe even better than we can.
It's a humbling thought, isn't it? And it underscores the responsibility we have in guiding the development of this technology wisely.
So to wrap things up, what are the key takeaways for our listeners today?
Well, first, ladder and TTRL represent a paradigm shift in AI with the potential to revolutionize countless fields. Second, we need to be mindful of the risks, particularly around bias and ethical implications. And finally, this is a conversation that needs to involve all of us. We need to engage actively in shaping the future of AI to ensure it aligns with human values and benefits all of humanity.
And that's a wrap for our deep dive into LDI. We hope you found it insightful, thought-provoking, and maybe even a little bit mind-blowing. Thanks for joining us, and until next time, keep exploring the fascinating world of AI.